So we're going to continue with reaction types. We've already looked at synthesis, decomposition, and single replacement. Now let's take a quick look at at combustion, and we're going to look specifically at the combustion of a hydrocarbon. And a hydrocarbon is just a compound of carbon and hydrogen, and it's a pretty common source of fuel. Sometimes we will add an oxygen to that. So an example of that would be an alcohol. An alcohol is a hydrocarbon that has an OH group on the end of it, which we know are also flammable. And the combustion of a hydrocarbon has to happen in the presence of oxygen gas. So you have to know that that's there. So if I were to, for instance, ask you what is the combustion of C2H6, you would have to know to put oxygen gas with that. Three things you need for fire, right, are heat, fuel, and oxygen. And then the products of complete combustion of a hydrocarbon are always the same: CO2 and H2O, carbon dioxide and water. There are other byproducts that you can get from combustion, either from impurities in your fuel, so it's not a pure hydrocarbon, or from a lack of oxygen, which is going to give you other byproducts. But if you have a sufficient amount of oxygen and you have complete combustion, then the products of combustion are fairly simple: carbon dioxide and water. Just as some quick examples, we already looked at a few hydrocarbon fuels. So CH4 is natural gas. We also refer to that as methane. Or carbon tetrahydride would be its covalent name. And that's the kind of gas you use to heat your home. Another good example here is C3H8, which is propane. So propane would be found in like camp stoves and sometimes like patio heaters. C4H10, 4-carbon chain is butane, and that would be like pocket lighters use butane as a fuel. And then a last example that we might look at here would be octane, which is the primary constituent of gasoline, so or C8H18. So those are some examples of some hydrocarbon fuels. So let's look at an example of a combustion reaction that you might want to complete. It says write the balanced chemical equation for the complete combustion of acetone, generally a liquid at room temperature, C3H6O. And so you want to start by writing out your hydrocarbon. You want to add oxygen gas. Your arrow to produce is going to be CO2 and H2O. So go ahead and write out that combustion reaction and then see if you can balance it. Go ahead and pause the video while you do that. Again, combustion reactions, fairly easy because the products are always the same products. So it's really a matter of balancing more than anything. So always start with balancing your carbons and hydrogens. Since you have oxygens in more than one spot here, it's kind of easiest to save those till last. You have 3 carbons on the left, you have 1 on the right, so we're going to need a coefficient of 3 on that CO2. We have 6 hydrogens on the left and only 2 on the right, so we're going to need a coefficient of 3 on that H2O as well. Now count up all of your oxygens on the right side. You have 6 from the CO2, 7, 8, 9 from the water. And then if you go to the left side, 1 of those 9 is in the acetone, so the other 8 have to come from the O2, which means the coefficient on that is going to have to be 4. If we had needed an odd number out of the O2, then go ahead and cut that, whatever the number is, in half and have a 0.5, but then you're going to have to go through and double the entire equation in order to get to a whole number ratio. So if you ever end with an odd number of oxygens, then you're going to have to double your fuel and then go back and rebalance the whole equation with that doubled fuel. All right, so that's combustion reactions. The last type of reaction that we're going to look at is called a double replacement reaction. So in the single replacement reaction, we had an element and a compound producing an element and a compound. And the element was kicking something out of the compound, a single replacement. In a double replacement, you have 2 compounds, typically ionic, and those ionic compounds each have cation and anion, and the cation and anion are going to switch partners. So let's look at an example. Here we have barium chloride in aqueous solution reacting with sodium sulfate in aqueous solution. Double replacement reactions are often carried out in solution because the ions, if dissolved in water, are free then to interact with one another. So see if you can't real quick write down the compounds, barium chloride and sodium sulfate, that are in our reactants. Again, go ahead and pause the video while you do that. Okay, barium is a 2+ charge, chloride 1- charge, so you should get BaCl2 on that. And then sodium is a 1+ charge, sulfate is a 2-, so you'll need 2 sodiums. So you should have gotten BaCl2, reacts with Na2SO4. We're then going to produce products where the cations and anions are going to switch partners. So the sodium is going to go with the chloride. Sodium is 1+, chloride is 1-. So you need to write the formulas before you go ahead and balance this thing. And then barium is going to react with the sulfate. And barium is 2+, sulfate is 2+, so it's just BaSO4. You got 2 sodiums on the left, got 2 chlorides on the left. You only have 1 on the right, so you're going to have to double that sodium chloride. You're going to need a coefficient of 2 there. The barium sulfate, notice, is a solid, so it's insoluble in water. And so sometimes you'll see that down arrow there next to that telling you that you had 2 solutions and you mixed them and then a solid was formed and it's going to settle down to the bottom. And we refer to that as a precipitate. So a precipitate is generally a solid that forms out of a solution. Well, how do we know that barium sulfate here is the precipitate? Well, if you look through your data packet, you're going to find a thing called a solubility table. And here is a slightly smaller version of that solubility table. And you'll notice when you look over here at the barium on the left and you go over to the sulfate above, where those two things meet, you have an S telling you that that thing is going to be a solid. If you try to dissolve it in water, it's going to be insoluble. Back when we were talking about some properties of ionic compounds, we say that a lot of ionic compounds dissolve in water, but certainly not all of them. And so barium sulfate is one that doesn't. And so in the double replacement reaction there produces from 2 solutions a precipitate of barium sulfate. Let's take another stab at this. So here's another reaction. So see if you can write this one out, if you can predict the products. Again, double replacement reaction. The cations and anions are going to switch partners. Lead to nitrate reacting with hydrochloric acid. Go ahead and pause the video, see if you can write a complete balance equation for those 2 reactants. So if you had a chance to take a look at it, here is the results. Lead is a 2+, nitrate is a 1-. Again, you can't balance equations until you have correctly written chemical formulas. HCl, or hydrochloric acid, hydrogen 1+, chloride 1-. The products then are going to be lead chloride, PbCl2. Again, the lead is 2+ and chloride is 1-. And then nitric acid, HNO3. Again, you have 1 lead on the left, you have 1 on the right, so you're good there. You have 2 nitrates on the left, but only 1 on the right, so you're going to have to double that nitric acid. When you do that, you're going to have to then double that hydrochloric acid to get 2 hydrogens. By the time you get to your last element, chlorine, you got 2 on the left, 2 on the right, and everything is balanced. Okay, let's take a look at another one. So go ahead and set this one up. See if you can get a balanced chemical equation. Okay, if you pause to try and take a look at that, let's look at the reactants first. Sodium nitrate, sodium is 1+, nitrate is 1-. Potassium chloride, potassium is 1+, chloride is 1-. Those are both AQ. If we look at our solubility table, we're going to find that both sodium chloride and potassium nitrate are also aqueous. And so what you have here is a situation where nothing has really been produced, because aqueous means dissolved in water and basically converted to ions. So everything here is still in its ion form on both sides, so nothing has really changed. Even though we can write an equation, we have sodium ions, nitrate ions floating around in water. We have potassium ions and chloride ions. On the other side, you essentially have the same thing. So if you start with AQ and AQ and you end up with AQ and AQ, you really don't have a reaction. You've just mixed 2 cups of ions and now you just have 1 big cup of ion. So kind of as a point about double replacement reactions, there are certain drivers of double replacement reactions. One is the formation of a precipitate. That will ensure that you are producing a particular chemical bond there because 2 things are going to form that ionic bond that are not going to dissolve in water. They're going to precipitate out. The other thing is the formation of a liquid. Typically this is going to be H2O, and this typically happens in acid-base neutralizations. And the last thing that you might produce in a double replacement reaction is a gas, and that's going to then bubble off. So you're not just talking about mixing 2 containers of ions, you're actually forming some kind of a bond there. And so if you don't have one of those 3 things, a solid, a liquid, or a gas, if it's just AQ all the way through, then a double replacement reaction isn't really a reaction, it's just mixing. So as a quick review on all our reaction types, here we have an element and a compound producing an element and a compound, so that's our single replacement reaction. If you have one thing breaking up into 2 things, that's your decomposition reaction. If you have 2 compounds producing 2 compounds, that's going to be your double replacement reaction. Carbon and hydrogen plus oxygen to produce carbon dioxide and water is an example of a combustion reaction or a combustion of a hydrocarbon. And then finally, we have the 2 things forming one thing, so that's your combination or synthesis reaction. So you should be able to identify reaction type even from just the reactants based on kind of these patterns of element and compound, a single compound, 2 compounds, right, or generally 2 elements are combining to form that combination reaction, and then the combustion reaction has the same products every time. So that covers all of our reaction types.